Hi, in this video I want to talk about a new approach for segmentation which is called clustering based segmentation, and I'm going to talk specifically about k-means method. So clustering basically is issued from machine learning, and it's used a lot in a lot of different applications. And one of these applications is, of course, image processing. So we can use that for segmentation to get different segments in the image. So the main idea is that the segments in the image would be represented by clusters in a given feature space, which can be made out of color or texture features, etc. Okay, so k-means clustering is typically applied on the RGB color space. Okay, RGB color space, and we try to find clusters in that space, and we try to find k clusters in that space. So k just refers to the number of clusters, and the mean, we have this term here because we use the mean property as a way to find these clusters. Okay, so I'm going to show you in a minute how this works. So it's difficult for me to draw a three-dimensional feature space of data points and just try to find clusters there. So instead I'm going to just do that on a two-dimensional feature space. So the first feature is R, and the second is G from the RGB model. I'm going to draw some data points to show you how this works. So I'm going to intentionally try to draw two clusters with some data points scattered around these clusters just to make it look more realistic. So the first thing that we do is we have, of course, to set the number k. So in this case it is obvious that we have two clusters. There are, of course, other sophisticated methods that can initialize k automatically according to the data points you have. But just for the sake of explanation here, let's consider that k is equal to 2. So what we do then is just we need to define 2 points, starting points. Okay, initialize the 2 starting points. So I'm going to consider, for example, the first point here and the second point here. Okay, and what I do then is just based on the position of these points, split the whole space into 2. Okay, so I'm going to split that into 2 by a line. So this line is just a line that is normal to that line and passes from the middle. Okay, so and then what I do in the next iteration is that I take all the data points in this region and calculate their means. Okay, and again do the same thing here, take all the data points here and calculate their means. And the reason why this works, the reason why this is useful, is because the mean tend to go to the center of the clusters. Okay, the center where we have a higher density of data points. So for the next iteration, we would hope that the mean or this point would move, for example, here. Okay, and again this point here would move probably here. Okay, and I do the same thing. I split into 2 and update the means, and at the end, hopefully, I would converge to something like that. The number or the second mean would be here, and the first mean would be here, and the line separating them is this one, and in this way, I would have got my 2 clusters. Of course, how do we know when to stop? So we stop when the 2 means that we have here do not move significantly. So we have to compare their position, current position, with the previous position. So if there is no significant change, we just stop the algorithm. So this is how it works, and sometimes it can get stuck, okay, because the mean does not necessarily move to the center of the clusters. For example, let's say that at a given point, the line separating these data points here is something like that. Okay, so probably because the data points here are evenly distributed, the mean would not change significantly. So even if we calculate the mean of these data points here, we would always get it, for example, here. Okay, and this is not true. This is wrong, obviously, because we do not get the clusters we want. So one way around that is to do several initializations. Okay, so I can, for example, take 2 points here, and then 2 points here, and then 2 points here, and do the same process, and then pick up the best result. And what I mean by the best result is the 2 clusters that have probably the, you can define some criteria or criterion. You can say the best result is the one that has where the cluster or the clusters have the smallest variance. Okay, so this can be a criterion to set in order to choose the best result. So this technique, normally k-means clustering, is used in image processing not only for segmentation. It can be used for other purposes. It can be used, for example, for compression. Okay, downsample the an image. So if I want to downsample the image and get only, for example, 60 or 30 color possibilities, then I have just to set k equal to 30 and apply this algorithm in this way. I can compress my image. It can also be used to split the image. It can be used as a splitting step. Remember, in the split and merge segmentation technique, I said that we have first to split the image. Okay, so I said that in the beginning we split the square into 4, and then we just go ahead and do the splittings by 4 by 4. We get at the end a quadratic tree. Okay, so another way to do the splitting is using this method, but instead of using only RGB as features, we have to apply some local constraints by including the x and y coordinates. So at the end, what we get is clusters. Okay, we get clusters, but are locally constrained. Okay, so they cannot be bigger than a given area. So we get clusters that are locally constrained. Okay, so something like that, and then we can do the at the end we can do the splitting and apply eventually the merging.